In the last segment, we discussed nonlinear maps, and we identified conditions under which the stability of a fixed point in a nonlinear map can be deduced from the properties of a linear approximation. Now, in a linear system, if you have an unstable fixed point, you end up with explosive trajectories that don't make a lot of economic sense. But in a nonlinear system, you can have an unstable fixed point and still have bounded trajectories, and these can exhibit complex dynamics. And we'll explore this phenomenon in the context of one-dimensional maps in this segment. Now, we've already discussed fixed points, and we now want to look at more complicated attractors. We'll begin with periodic orbits or cycles, which, like fixed points, can be stable or unstable. And we'll discuss how we can determine the stability of an orbit. And then we'll talk about more complicated attractors called chaotic attractors, which are neither fixed points nor periodic orbits. So consider a dynamical system xf, where x is a subset of the real numbers and f is a continuously differentiable function. We say that a periodic point of f with period n is a fixed point of the function f to the n, and a periodic orbit of this system with period n is an array of points x0, x1, all the way up to xn-1, with the property that each point in this array is the image of its predecessor under the function f, and x0 is the image of xn-1. So if you start off at any one of these points, you'll end up every n steps returning to the point at which you started. Now, just like fixed points, orbits can be stable or unstable, and we want to think about the conditions under which we can identify stability of an orbit. To do this, let's start by defining a function g of x, which is f to the n of x, and note that every point in a periodic orbit must be a fixed point of g. Now, one way to check for the stability of an orbit is to check for the stability of every single point in the orbit, and we know the conditions for this. The fixed point xi of g is stable if the absolute value of the slope of g at xi is less than 1, and unstable if that slope is greater than 1. So a periodic orbit will be stable if each point in that orbit is a stable fixed point of g. But actually there's a simpler way to check for stability of orbits. We don't need to check this condition at every single point in the orbit. It's enough to just check it at the point x0, or in fact any other point. And this is because the slope of g at x0 is the same as the slope of g at x1 and at every other point in the orbit. And you can see this very easily as follows. Note that g of x0 is equal to x0, since x0 is a fixed point of g, and this in turn is equal to the image of xn-1 under f. And the image of xn-1 is just the image of xn-2 under f, and proceeding in this manner you get the expression shown on the slide. Now we just apply the chain rule and differentiate both sides to get the expression on the slide, which says that g prime of x0 is just the product of the various f primes evaluated at the n different points of the orbit. Now this expression is symmetric. You can start at any point in the orbit and you'll get the same product. And this means that the slope of g is the same at every single point in this orbit. So to check for stability of an orbit, all we need to do is to check for stability of a single point under g. So we can summarize this as follows. A periodic orbit is locally asymptotically stable if the absolute value of the slope of g at x0 is less than 1, and it's unstable if that slope is greater than 1, and you could replace x0 in this expression with any of the points in the orbit. Now, even if all the fixed points of our original dynamical system are unstable, they may be stable periodic orbits. And here's an example using the logistic map with parameter a equals 3.2. Now, if you look at the graph of this map, it has an inverse U-shape. And if you look at the intersections of this with the 45-degree line, you see the two fixed points shown here in red. Now you can verify that both these points are unstable. So what happens if you start at some seed that isn't a fixed point of this system? What's shown on this diagram is the orbit you get if you start at the seed x0 equals 0.05. To read the diagram, you start off at the seed, go vertically up towards the function, then horizontally across to the 45-degree line to get the second point in the orbit, then repeat this to get the third point, and so on. And you'll see that in the limit you converge to a stable periodic orbit with period 2. Now let's consider attractors that are more complicated than periodic orbits. So now consider the logistic map with parameter a equal to 4. Now this map has two fixed points at 0 and 3/4, and they're both unstable. To see this, look at the image at the top left of this figure, and here you see the function f along with the 45-degree line, and here you see the two fixed points shown in red, and you can verify that these are both unstable. Now let's think about orbits with period 2. To identify these, look at the image in the top right of this picture. And here the image is of the function f iterated once. Now obviously the fixed points of f have to be fixed points also of f squared, and these are shown in red. But in addition you have two new fixed points of f squared, and these correspond to a periodic orbit with period 2. Now you should verify that the slope of the function at these 2 points is the same, and indeed that it's greater than 1. So therefore the periodic orbit with period 2 is itself unstable. So to summarize, the map f squared has 4 fixed points. 2 of these are the original fixed points of f, and the other 2 correspond to a 2 cycle, and this 2 cycle is itself unstable. Now what if we iterate this map 3 times? That's shown on the bottom left of the figure, and here you see 8 fixed points. 2 of these correspond to fixed points of f, but the remaining 6 correspond to 2 3 cycles. Now you can identify the 2 different 3 cycles by using the fact that the slope of the function at all points in a given cycle must be the same. So the original fixed points here are shown in red, one of the cycles is shown in green, and the other cycle is shown in blue. So to summarize, the map f cubed has 8 fixed points. 2 of these are the fixed points of f, and there are 2 3 cycles. And in fact both of these 3 cycles are unstable. And we can continue in this way. If you iterate 4 times, you'll find 16 fixed points. 2 of these are fixed points of f, another 2 of them are fixed points of f squared, so that's a 2 cycle. And the remaining 12 points of f to the 4 correspond to 3 different 4 cycles. And you can verify that these are all unstable. Continuing in this way, you see that f to the n has 2n fixed points, so you have an infinite number of periodic orbits. And all of these are in fact unstable. So if all periodic orbits are unstable, then what do trajectories of the system look like? I'll begin by showing you a simulation, and then we'll think about this more analytically. The 4 images in this picture all correspond to trajectories that start off with the same seed. The image on the top left shows you the first few steps in the orbit. The one on the top right shows you a few more, and so on. So all these pictures are describing the same orbit, but truncating at different lengths. And you can see that there appears to be no tendency to converge to a periodic orbit. Now, although it looks from the diagram that this trajectory is visiting every point in the unit interval, that's not possible. It's clearly not visiting any of the fixed points, otherwise it would stop there. And it's not visiting a periodic point either. But nevertheless, it does look like every open set in the unit interval is being visited by this trajectory. So how can we express this idea a bit more formally? We'll do this as follows. Let I denote a closed interval in the set of real numbers. We say that a self-map f on I is chaotic if it satisfies 3 conditions. First, if the periodic points of f are dense in I. Now recall that a subset S of I is dense if every point of I is either contained in S or is a limit point of S. Second, if you have 2 subintervals, I1 and I2. Now these could be open or closed, but they should have positive length. Given any 2 subintervals, there's a point x in the first interval and some number n, such that if you start at x, then after n periods, you'll reach a point in the second interval. This is referred to as transitivity, and it basically says that if you have 2 intervals of positive length, no matter how small they happen to be, you can always reach one from the other after some number of steps n. And the third condition, which is called sensitive dependence on initial conditions, states that there's a constant beta positive, such that for any x in the interval I, and any open interval u containing x, there's some other point y in u, and some number n, such that after n steps, the distance between the orbit starting at x and the orbit starting at y will exceed beta. Now think about what this means. It says that no matter how close x and y happen to be to each other, their orbits will not remain close, in the sense that they'll separate by an amount beta eventually. And if a map satisfies this condition, then even the smallest error in measuring the initial state of the system will lead to forecast errors in the long run that are at least as great as beta. This is what makes chaotic systems very hard to forecast, at least beyond the short run. So if you think about phenomena that are subject to complex dynamics, like hurricanes or tornadoes, or even economies for that matter, even in the absence of shocks, these would be very hard to forecast except in the very short term. Now I'll just note that the third condition, sensitive dependence, is redundant for maps on an interval. The first 2 conditions imply the third when we're dealing with maps on an interval. Now I'll end this segment with the claim that the logistic map with A equal to 4 is chaotic on the unit interval. So it satisfies these three conditions. Now before we think about the proof of this, let's just think about the intuition. Look at the first two conditions. We want to show that the periodic points of the logistic map are dense in the unit interval, and we want to show that transitivity holds. If you have two intervals I1 and I2, you can find a point in the first that will lead you eventually to a point in the second after some number of steps n. So to think intuitively about why these two conditions hold, let's go back to our diagram with iterated maps. Now we've already seen that we have an infinite number of periodic points. And to see that the set of periodic points is dense in the unit interval, just note that any open set in the unit interval must contain a periodic point if you iterate this function enough times. So the first condition for chaos should hold. Now for transitivity, note that if you take any open set in the unit interval and you iterate this map enough times, you'll reach a point where the image of that open set is the entire unit interval. And if you think about this, you should be able to see that for any two intervals I1 and I2, you can find a point in the first and a number n such that the image under Fn of this first point will lie in the second interval. In other words, transitivity also holds. Now this is not a proof, but it gives you the intuition for why the result might hold. So let's think about the proof, and I'll just sketch it with some missing steps that you can fill in. Consider the systems xf and yg, where x and y are intervals in the set of real numbers. Now we're going to weaken the notion of conjugacy a little bit. Suppose that there's a function h, which is a continuous surjection from x to y, that is at most n to 1. So it doesn't have to be 1 to 1, but it's at most n to 1 for some number n. Now suppose that this function h satisfies the conjugacy equation, h composed with f equals g composed with h. Then we say that h is a semi-conjugacy between f and g. Note that if n is equal to 1, then we have a conjugacy. If such a function h exists, and f is chaotic on x, then g is chaotic on y. So to prove that any map g is chaotic on y, all we need to do is to find a possibly simpler map f, which we know to be chaotic, and a semi-conjugacy h that connects these two systems. Now to apply this, consider the tent map. It's a very simple piecewise linear function that maps the unit interval onto itself. Now if you think about what this map looks like and what its iterates look like, you should be able to verify very quickly that it satisfies the conditions for chaos. So to finish up, all we need is to find a semi-conjugacy between the tent map and the logistic map with a is equal to 4. And the function h shown on the slide is in fact such a semi-conjugacy. Now to show this, you need to dust off some of your high school trigonometric identities, but it's a straightforward matter to verify that this function h satisfies the conjugacy equation shown at the top of the slide. H composed with t, which is the tent map, is equal to the logistic map with a equal to 4 composed with h. Now to complete the proof, you need to verify this, and to verify that the tent map is in fact chaotic, and finally to verify that if a semi-conjugacy between f and g exists, then f being chaotic on x is sufficient for g being chaotic on y. If you fill in these gaps, you'll have completed the proof of the result shown here on the bottom of the slide, that the logistic map with a equal to 4 is chaotic on 0, 1. Now to finish up this segment, let's just think about the implications of what we found. We've seen that even in the simplest case of a one-dimensional map, you can get complex dynamics when you have an unstable equilibrium and nonlinearity. If you want to see examples of economic models that generate trajectories like this, you can look at Grandmont's paper in Econometrica 1985 called Endogenous Competitive Business Cycles, or an even earlier set of papers by Benhabib and Day. And all these papers show chaos in an overlapping generations framework. But the general point is not that one-dimensional maps are useful in economic modeling. It's that it's possible to get complex dynamics if you combine local instability with nonlinearity. And what you can find in one-dimensional systems, you can easily find in higher dimensional systems. Now I'll just mention that for differential equations, you can't get complex dynamics in 1 or 2 dimensions. You need to move to 3 dimensions or higher. But you get very similar kind of properties once you enter the realm of higher dimensional systems. And I'll stop here for this segment.